Where was the meeting? Oh. Yes.
Yeah, all right, we should get started. Because I want to make sure we get through a little overview.
Thank you.
Quick announcements. At this point, we all know what's happening tomorrow. Hopefully that's not news.
It's fifth Monday.
We'll have an exam. Homework, the last homework is graded. It's just not revealed, I think. I learned my lesson last time. I'm not going to reveal it right before the start of class to distract everybody, but I will do it right after class so that you can take a look at it and come visit office hours if you have any questions or concerns about it.
It's revealed.
I think it is revealed.
It got revealed. Perfect. All right. Well, in that case. Yeah, Harley messaged me last night. It's like I hit all the grades, and then so I was going off that. I didn't actually check this morning. Look good at others. So I will have office hours after class. That will be, feel free to come ask any questions about the homework. So we have, I think, 4 practice problems left to do. So we're going to first look at. We're first going to look at countable and uncountable set types of questions. So first one of these. Is the set of all finite length binary strings countable? If so, think about a procedure that would enumerate them. First of all, is this an infinite set? Are there an infinite number of finite length binary strings?
Yes.
Yes. What do we think?
No, it's just like. I think it's not.
It is countable. It's good. How do we enumerate them?
Another A process. If you start with 1 and then 0. And then for 1 and 0, like from there on, for 1 and 0, you just place the 1 or the 0 and then repeat everything that's already in the list. Like following that 1 or 0, and then you'll get everything.
All right, would be one way to do it. Any other ways that we could enumerate and make sure that we count them all? Yeah, that's the one I was thinking of. So we have something like 0 and 1. Those are the only possible binary strings of length 1. And we can go through all of them of length 2. So we have 0, 0, 0, 1, 1, 0, and 1, 1. How many are there going to be of length 3? Two to the third, 8. That would be right. So this is 2 to the first. This is 2 squared. 2, that's a 2. We have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 0 0, 1 0 1, 1 1 0, and 1 1 1. Those would be all of the binary strings of length 3. You can also think of each one of these as like flipping a coin that many times. How many outcomes are there? So you could map this onto anything binomial that you've seen in a statistics course or. But this process, if you did all binary strings of length 1, length 2, length 3, length 4, etc., you would just continue to output them. To know whether something is countable or not, you want to think about, is there a counter example that someone could give me that my enumeration algorithm would never output? So could you come up with a binary string where if I followed this process forever, it would never generate? And the answer is no. This would eventually generate any particular binary string that you gave me. So that tells us that it's a complete enumeration procedure. It will generate, it won't finish, but it will generate any particular binary string. It won't generate them all because they're an infinite number. But it's a complete procedure if we had infinite time.
I'll make a question on like the exam. How would we write that out? Just kind of as like a little explanation.
Yeah, I would just say something like all binary strings of length 1, 0, 1, all binary strings of length 2, etc. Continue this for all positive integers. And you would have a complete algorithm. So now let's find a language that's a subset of this. What if we said all binary strings that start with a 1? You could use a very similar procedure to this, but the question that I would want to ask you is this language recursive, recursively enumerable, not recursively enumerable? What would that language be? All finite length binary strings that start with a 1.
Would it be recursive?
What makes you say it's recursive?
Well, you can tell if something is, you know, if it is something, well, if it's just like, for the definition is like, we want things that, what did you say, start with 1? Or,
Yeah.
Okay, would start with 1s. You can say, yes, it starts with a 1, and that's within the language or whatever, so that's a yes for that. And
Yeah,
then
we
you
need
can
to
also
answer
say-
2 questions.
You can also say, no, it's not one that starts with a 1, and then it's also countable because it's also like a subset of something that we just proved essentially that is countable, so it should
Yeah.
all work out.
Yeah, assuming the input is a finite length binary string, it is recursive. If we allowed these to be infinite length binary strings as input, now we wouldn't necessarily be able to say, no, it is or is not a finite length binary string. So assuming the language is all finite length binary strings, then yes, it is recursive. But as soon as you were to say something like we allow infinite length, then we would never have a procedure for making sure that the number terminates and starts with a 1. It could be that we just cycle forever as we look at this infinite length binary string. Speaking of infinite length binary strings, we'll look at that one next. So yes, the answer is it is recursive. If the possible set of what could be given is finite.
What's the third option? Recursively enumerable.
Not recursively enumerable.
And that means.
You can't answer yes or no. Or you just, it's undefined kind of, you can't answer yes.
Could run forever trying.
Yes.
That's right. We're talking about.
What do you think?
No.
Not countable? What makes you say that?
So you can do the diagonalization.
Yes, it's very similar to the real numbers. So you have the same kind of proof by contradiction that you had with the real numbers. So where you say, assume that this is countable and we have a list. It may be an infinite list, but there's some algorithm to producing this list. And all of these infinite length binary strings, there isn't a number that you could give me that doesn't have an associated index in this infinite table. You give me a number, it has an index in it. If you make that assumption, then we do some kind of diagonalization proof where this continues forever. This continues forever. We have, some number 1100011101111101011, etc. I wrote way too many numbers, but you have a second number that's you take the first index of the first number and you flip it, and this says that this is distinct from this number. You take the second digit of the second number and you flip that, so it's distinct from the second number. And you continue this process, since this is infinite and this is infinite, you will be generating via this process some number that is not in the table. Either of these processes will terminate, but it's not complete because you can go through a process to come up with something that is not in the table. And if you feed that number into here, there's no associated index for it. So that's what tells you that this is not countable. There does not exist an algorithm to enumerate all infinite length binary strings. What does that mean with regards to its language class? If we wanted to put this on the Chomsky hierarchy, where would it be?
Should be recursively enumerable, I think.
If it is, then we would have some process of being able to say, yes, it's in the language. And because it's infinite length, that process would never terminate. Yeah, it's beyond the scope of recursively enumerable. We can't enumerate it at all. It's, not recursively enumerable, outside of the realm of, it's outside of the Chomsky hierarchy. It's so general that we can't even answer if a particular string is in the language or not.
So most things so I just want to have some clarification here, because I obviously answered incorrectly.
Yeah,
So if something isn't like in this example, this isn't countable, and we can figure out it's not countable by this diagonalization proof.
yeah,
Whatever it is called. If we can't count it with the diagonal, or we show that it's not countable via the diagonalization proof, does that also now mean that it does point us, or at least it does say that it is not recursively enumerable?
Yes.
That is what okay.
yeah. So we talked before about recursively enumerable. An example of that was like the rational numbers, where we could take kind of a diagonal wavy line through the numerator on one axis and the denominator on the other axis. And each element of that two-dimensional array gave us one particular rational number. We could figure out some way of then saying yes to, there's a way to generate all such rational numbers, or the better way to state that is there does not exist a rational number that this algorithm would not generate. So we can say yes, but then we include something like pi, and we ask, is pi rational? And this algorithm will never be able to tell us, no, it is not rational. Which means that there's some supercomputer out there calculating digits upon digits of pi right now. And if that process ever terminates, then we know that pi is either it's rational, it ends, so there exists some numerator and denominator that represent it, or if it starts repeating, then there would be it would represent some rational number. So if we ever figured that out, then we would know that it is, but there's no way to know that it's not. It could just continue spitting out digits literally forever. never stopping, never repeating, and we would never be able to answer the question of, is it rational? Because we don't know if it's just not done yet. So that's recursively enumerable. We can answer yes if the process terminates, but we can't answer no because we don't know if it just hasn't terminated yet or if it's stuck in an infinite loop. Or it just doesn't terminate for some reason. So there's no way to even start counting these, to enumerate them, to spit them out. There's no process that we could come up with that would be complete for spitting these out. Questions on this? Last one for you. The set of all languages that are not recursively enumerable. Is that countable or enumerable?
Like not even meant to.
So I heard one no. What intuition do we have for this? Yeah,
I mean, I might not have the language to, the literal, like,
That's fine.
speech to convey what that is, but like, so if you have one not recursively enumerable thing that isn't countable.
Yes.
You can essentially just like add another language, like show that there's a language that is not that. And then you can kind of iterate or like expound upon that process, like kind of using the, like, how we showed that like the infinite length binary strings aren't countable, we kind of do the same thing.
Yeah.
The bigger idea of the concept of recursively enumerable things not being countable, and so you can say like we have a language, this one isn't countable, like we can't count this because like we need to make another recursively enumerable thing, and you can kind of expound upon that. And it maybe through the Chomsky hierarchy, you can kind of show that like it kind of can get larger and larger, maybe.
Interesting ideas for sure. It's good. Any other thoughts or ideas?
It's just my intuition is like, well, instead of all languages that are not recursively enumerable, that includes those sets that. The set of recursively, or recursive languages.
No, because those are also recursive.
Oh,
So basically, we drew the Chomsky hierarchy. Yeah, we drew the Chomsky hierarchy, and this is just a, you know, a very small, way too few levels of it. But could we identify every language that is outside of the Chomsky hierarchy in some sense? If we had some way of turning computation or things that we cannot compute, because that's what outside of recursively enumerable is. We can't even answer yes to it. So is there a way to figure out all of those languages or enumerate what all of those languages are?
It would be every language that we can't enumerate, so if you enumerate all the enumerable languages. The whatever, the complement of that will be that set.
But would we ever be able to answer and generate those languages? So we could identify basically if we had a way of generating what is determinable, we could eventually be able to say it is not determinable because of that. But we'd have to be given a query language for that, right? To be able to say, can we enumerate all of the languages? And then we could identify for a particular language. But then how do we know if we're done generating those languages? Or how do you define a process to generate those languages where when you compare them to all the computable languages, you get no?
I think I'm gonna have to go with the definite no.
The answer is no. This is not countable.
It feels like people and people thing.
I wanted to throw this on there just because it's kind of the single most theoretical question you can ask. Can we know what we don't know? Is basically the question that it boils down to. Can we know things that we can't know? And the answer is no, of course we can't. But it creates a nice, easy way to say, what is the class of languages where we can't answer anything about it? We can't determine membership or non-membership, but we can at least have a definition for it, like all infinite length binary strings is one such language. But what process would generate that language? It's just not gonna happen. So this one's more of a fun question than one that I would actually ask, because there's no real procedure for answering this, given what we've given, but it's just more of a fun, understand the concept of what is not recursively enumerable, because that's just so theoretical. It's the stuff we can't calculate, the stuff we can't answer anything about. All right, any questions about recursive languages, recursively enumerable languages, non-recursively enumerable languages, countability, decidability? Computability? All right, the last question that's on here is the last Turing machine question from a while ago, so we're gonna go back to that. So now we're going to design a Turing machine to add 1 to a binary number. So on the input tape, there is a binary number, and we want to figure out how we're going to add 1 to it. So the output on the tape afterwards should be that original input number, but 1 higher.
Oh.
So we had an input tape that was just 0. Then the output to that should be 1. If we had a tape with 1 1 1 1 1 1, then the new output, see 1 0 0 0 0 0 0.
Only need one.
Sorry.
So there can only be one. One.
Oh, there could be more than that.
Oh.
If, for instance, let's give you one more example. If the tape is 1 0 1 0 1 0 1 0, and the output to this would be 1 0 1 0 1 0 1 1.
On the, are you gonna, like, do we need to be very specific with like, using like the delta transitions notification?
If I can figure out what your transitions are, then there's probably significant credit there because I care more about the logic than I care about the precise notation. But the precise notation will make that process the easiest for the grader / myself to be able to see and understand the process without having to look at a key. If you're going to deviate from that delta notation or a state machine that we've talked about before with the same kinds of transitions that we've seen on homework problems or in the book, then just make sure you include some kind of key.
So right now, I said yes, and then I'm like, let's get it out of that.
Yeah,
Can you say start at the rightmost?
you cannot. You would have to determine a couple of transitions to get to that point.
I wonder if there was a shortcut.
I think that's just 3 transitions though.
Yeah.
When you showed it to us yesterday, I thought it was gonna be a little more complex than it is.
It's not too bad, huh?
Is it safe to assume? Well, it won't really matter, but is it safe to assume that it'll always start with a 1?
I would say that it's not safe to assume.
Okay. I guess it won't change how this works, but. I don't know why you would pass in a binary number that doesn't start with a 1 unless it's just a 0.
If you're reading memory instructions and you have a certain, like an integer is gonna have many leading zeros probably.
That's a good.
The plus algorithm. Something we've taken for granted is something that's really easy throughout our entire programming careers. Luckily, we're assuming everything is positive here, but if it was actually in 2's complement, then it would be a little bit more difficult. Anyone have an answer they would like to come right up on the board?
Getting close to an answer. That's done.
Excellent. Well, if I don't get a volunteer in the next, between now and when you finish, you're welcome to volunteer.
God. I'm barely. Space and transitions on board. Takes so much time, I'm like, that's terrible.
So how did people who have an answer handle the carry logic?
Very much. You just go. And go over the ones, replacing them with zeros until you use a zero, and then that becomes a one.
Yep.
Or if you have a blank.
Yep.
I came right up.
Yep. Good.
I could write up my one.
Nice. Thoughts on this Turing machine? It does not return to the beginning.
Need to return to the beginning.
If the output is on the tape, usually the best thing to do is to put the head back at the first character of the input, so you're ready to read exactly what that is.
When do you want to
Oh,
end on the right side? Because I thought that was the typical.
Put it at the end, you mean?
Yeah. Yeah, I get that the right mostly at the end.
Yeah, so the reason for that would be something like if you needed to read the answer or actually output the answer to something, then the Turing machine, there's a program for iteration that you could just load and run into the Turing machine that says output whatever is on the tape until you output a blank. And that becomes the output that you can feed to somewhere.
So yeah, just to add on to that, it seems like some of the homework stuff that we've gotten on other examples or whatever we talked about in class that like. It didn't really matter where you had the head, like normally, like the normal convention that I've been doing is obviously leave that towards the right at the end, and then for this one, you're saying. Leave it to the left so that if you wanted to add another, I guess, so are we always having to think about the context of what position we need to leave the head at?
Sometimes that will be problem dependent. If it's an acceptor that's answering yes or no, all that matters is the output yes or no. It doesn't matter where we are on the input tape because the input tape doesn't contain any relevant information to the output. Whereas if this is a transducer and we actually care about the output that's on the tape, then we need some way to know where does that output begin. And you could have in the process of doing your computation, the output is just a portion of the tape that ends with a blank, but there's some other work that you did to the left of it that is not relevant. So the Turing machine program would tell you, here's where the answer starts. And then a blank would tell you where the answer ends. Kind of like a C array,
So
a C string.
would that be a thing we lose points for on the test? If I were to like put that as opposed to moving it all the way back to the left?
I will probably tell Harley that this is not particularly relevant to the exact answers on it. It's more of a, if you're going to implement this. For real, then you would want some way to be able to output or identify where the answer is. But I think this level of logic is good enough to just what I'm interested in is, do you understand how to write the transitions and solve a problem with the transitions? Not do you add one little addendum at the end to get everything back to the beginning?
I just want to be sure here though, so for it to terminate, it does need to end on a blank, right? Or like touch a blank?
Terminate,
Yeah,
terminate the output, you mean?
yeah,
That's how I would read it. So if you think like a C string is just a character array. Where you read until you hit the null character, and then the null character tells you that you're done with that. So C strings and character, they don't have lengths. They just have a particular starting index and they read until the null character, and the null character tells you when you're done.
okay, but am I allowed to terminate on a different character if I wanted to for some reason?
You would easily be able to change that Turing machine to another one where you say the first character of that I see, turn that into a blank. So you could basically do that in the short term, and then you could have another target program that goes and turns that character into a blank.
But if I didn't turn that character into a blank, would that be a valid like halt? Or does it have to halt on a blank?
So it can halt on anything. It's just the end of the input is what should be, or the end of the output on the tape should be a blank.
Okay,
So like if the next character after each one of these and the output should be a blank that tells you that that's the end of the output. If we had something like Z or some other character that was not the blank, then how would we know the difference between we want to output the letter Z versus we want to finish the output and not output anything more? There would be no distinguishing characteristic. The blank is a symbol that basically means the equivalent of C or C++'s null character.
okay,
It has no display purpose other than as a terminating character or a nothing character. So that just matters if, for instance, we wanted to output what was on this tape and use it as input to another program. We would need some way to read what's on the output tape and export it. And that's what the head would do. It would start with where it is in its halting state. It would just it'd be loading a new program that is starting here and reading until you get a blank, output this to some other location. And that's how we would get this off the tape.
okay, just one more question.
Yeah.
Because I'm trying to think like if I want a program where it's a Turing machine that accepts every string that has 5 or more ones. Could I make a machine where after the 5th one, it just halts right there? It doesn't even bother to check the rest of the strings?
Yes. And the reason is that it's an acceptor. It's an acceptor or rejector and not a transducer. We don't care what's on the output. The goal is not to output the string or anything to do with the string. It's to say, yes, the string that was on this tape has 5 or more ones, or no, it does not.
Okay,
So the placement of anything on the tape doesn't matter. We don't need the tape for anything after that, yes or no.
okay.
Great question. All right, that was the last planned practice problem. Does anyone have any other clarifications from the study guide? Anything else I can go over? Anything that you're unsure about? Or would like extra practice with if it's something I can generate off the top of my head?
Maybe just other things not countable, basically like computable or decidable.
Something that's not computable or decidable?
Well, maybe not like either yes or no. But just like one of those questions.
Yeah.
We saw one on the homework, we saw countable.
Yeah, so lots of countable. That matters more because it actually has, it affects what we can or can't, what we can do in ways that we can iterate it. But I would say that in general, something is not countable if you can end up with some kind of diagonalization. You do a proof by contradiction, basically saying, assume that we can enumerate this. Here is a procedure for generating something that this enumeration wouldn't generate.
What are the applications of a Turing machine?
So, okay, yeah, Turing machine represents, it's a theoretical
Yeah.
machine that represents what we can or cannot program. So it allows us to say, basically, if we had infinite memory, what is possible and not possible? And if we wanted to say if we have a finite amount of memory, then we could do something like a linear bounded automata that only uses the amount of input, the amount of space that we use for the input to calculate it. You could bound it to something like we have 16 gigabytes of RAM, we have 16 gigabytes of space on this tape. What can we do and can't we do? But of course, that would only work for finite languages. Because most of the languages we've studied this quarter have been infinite languages, and infinite languages can be even something as simple as a to the n, b to the n. That can consume more than 16 gigabytes of RAM for an n that is sufficiently large. So we're able to answer things in general about languages if we assume we have an infinite tape. But in reality, we don't have an infinite tape. We have a very large but limited tape.
What kind of questions, or like, could you give us an example question for like unrestricted and context sensitive grammars? And or, I guess.
Yeah, so I think I mentioned that I'm not gonna have you generate those kinds of grammars just because they're really difficult to generate. But if I gave you one such grammar and then asked you, can you determine whether this is in the language or not? Could you expand the grammar with those rules to produce that string? So just be able to use an example grammar to answer questions about that grammar. The other thing that I might ask with a context sensitive grammar is, here's a grammar, is it context sensitive? Basically, does this adhere to the rules of a context sensitive grammar?
That first part that you just spoke into about given some sort of string. And it's an unrestricted grammar, you said expound on that, so that is more just like. We would just be kind of doing a flow of consciousness of what we think about and like see if we arrive at the right conclusion, like if you.
If you like apply the productions, kind of like an instantaneous description where you go through the process of deriving that string in that grammar.
Okay, so that's what you're talking about, okay.
Yeah,
All right.
some kind of derivation. And I would make sure that it's intuitive enough that it's not just a bunch of replacements. A becomes B, B becomes C, C becomes AB becomes that you can do that in unrestricted or context sensitive grammars, and it's kind of unintuitive. The way that I like to explain it is, yeah, a few minutes we can do this. Context-free grammars kind of build on themselves in the way that object-oriented programs do. I think I mentioned this in office hours yesterday, but not everybody was there for that. So at the very low end of objects and object-oriented programs, you have primitives. You have, some int and some float, and the combination of that produces some object. And then we have a float, and a character, who knows? And you combine all of these things into another object. And you can compose some object C as this hierarchy. And you basically get objects that are composed of other objects that eventually break down into primitives. And this is very much like a context-free grammar, where you have a non-terminal that is defined to be more non-terminals that are eventually defined in terms of terminals. And that's what ends the process of creating grammar. So it's very much like object composition. What this doesn't allow us to do is teleport around this diagram and do replacement and say, A, instead of being this object, can now be D, this completely other object. This just says we can replace A with D. This is not a hierarchy. Now we have the ability to teleport across this. And this is what we introduce in context sensitive grammars or unrestricted grammars. Is we get the ability to actually take a substring and completely replace it. So wherever we see an int float, we can replace it with an int. And that's just wild to think about, that you can just do replacement like that without context of why we're doing that. Whenever you see this, it can also be this completely unrelated thing. That makes sense as to the difference. I hope that intuitively explains some of what we've been doing.
Yeah.
Other last minute questions? It happened yesterday afternoon. That was more than 5 seconds ago.
Fair enough.
If I unplug this, I can tell you.
Let's not unplug it.
So how many questions are on the agenda and how many questions are asked?
Yep. Let me actually tell you that. There are 110 points. It'll be graded out of 100. There's question 1, question 2, question 3 that has 3 parts, question 4 that has 7 parts, question 5 that has 3 parts, and that's it. 7-parter.
Kind of question is that 7 partners.
You'll find out tomorrow.
Question and clarity. It has 3 parts. That may be 7.
I mean, it's gonna be all 7. We don't have to do like the formal definition thing.
No.
No, okay.
You just have to do the transitions.
Specifically didn't have to do that.
Yeah, I'm not gonna make you do something you haven't had to do for homework.
So no uncountable sets, got it.
Maybe, maybe not. I'm not gonna make you choose a form that was not there. With 3 minutes, do we really have time to do anything new? Do we want to go over 1 slide in 3 minutes, or do we want to call it 3 minutes early?
3 minutes. Really?
That's true. All right, we'll get out of here 3 minutes early.
I don't want to learn about.
We'll pick this back up next week.
I know so much about this now, but I also.
And I'll see if I can. People wanting to stay.
So I got the number. I got it. So,
Oh, nice.
I think I'll just send you the.
Yes.
Yeah, that would be
Yeah, that's awesome.
because I'm gonna redo them today. I'm gonna redo all the homework questions.
Yeah.
Right, so it would be good to be able to compare what I get to what you have.
Because especially I have one trade machine. I have guides on what
Well,
transaction
that would be that.
for every single transaction.
That's
So that
great.
would be a-
Yeah, that would be so cool. Thank you.